Hello, everyone. I'm Sebastian, and today I'll be talking about preserving diversity when partitioning, a geometric approach. This is joint work with Victor, the University of Higgins, and Alfredo at Polytechnic Montreal. Okay, so the motivation of this work is something that is happening right now in Chile. We're rewriting the Constitution. Our current Constitution was written in 1980s under the dictatorship of Augusto Pinochet. And recently, we decided to write a new Constitution that actually represents the Chilean population. So for that task, we elected 155 members via popular vote. And they have to draft a new Constitution, and later on, this Constitution will be ratified by another election. So from time to time, these 155 members have to split into groups to write different chapters of the Constitution. And the question that concerns us is, how can we split the members of this group into different groups such that the political viewpoints in each of this group is represented as much as possible? Or in other words, how can we maximize the political diversity in each of the groups? For some members of the audience, it might be self-evident why we need political diversity in writing the Constitution. But just to give you one point, basically, we would like to have everyone represented in the task of writing the text. And also, we don't want that a political party or a political sector to write part of the text in their own self-interest. But the benefits of having a diverse group or diverse teams go beyond these applications. In 2015, McKinsey was reporting that even diverse workplaces in terms of ethnical diversity and gender diversity were performing much better than their less diverse counterparts, even under very basic metrics of diversity. Now, there is a question here. We all know more or less what diversity should be, but there is the issue of how to measure diversity. And there's been many approaches over time. And I would like to mention one of them here, which is dissimilarity metrics, which tries to deal with how different two entities or two people are in a population. And the one that we consider in this work, which is a sample-driven metric, which is mostly used in ecology settings. So in this work, we decided to work with the sample-driven metric. And in 1948, Simpson introduced the following index in the following setting. So we have a population of entities, and this population is divided into different types. So the index measures diversity in how likely is that in two consecutive trials, you are how likely you are to draw two entities of the same type, which is the formula that I'm showing down here. So R is the number of types, and PI is the fraction of entities of type I. In practice, scientists don't use this number, they use the inverse of this number, because this probability is minimum when everyone is uniformly distributed. We have evenness in the population, and is maximum when one type dominates all the other types. So the inverse of that holds the inverse of that property, so it's maximum when everyone is when the population is even. So just to give you an example here we have a population of 6 circles and 4 triangles and 8 squares. And the current effective number of this population is roughly 2.79. But if we increment the number of triangles, the effective number increases to 2.88. As I said before, the effective number satisfies the evenness, but it also satisfies other properties that are desirable when people study diversity, such as continuity and also symmetry. In this talk, I'll refer to the effective number just simply as diversity. So as I said before, diversity is maximized when evenness holds. And with this language, and with this work, what we did is that we introduced a model to study how diversity deteriorates when we partition a community into different subgroups. And we study mainly two questions. The first question is, how can we split this community of entities in such a way that each of the group is as diverse as the original as the whole community? When we cannot do this, when we cannot guarantee a diversity as diverse as the whole community, we consider a more relaxed question, and these questions try to deal with maximizing the least diverse community. In the rest of the talk, I'll be formalizing the model, and I'll be giving you the answers of this question that we find in this work. So the formal model, the mathematical model, is that we have a population of size n, and this population is divided into R types. The information is given to us by a vector B. The vector B contains the number of types. So BI is the number of entities of type I. We measure diversity with the effective number, or the Simpson effective number, which we can reformulate as this ratio of norms. And the goal is to split the population in such a way that we can maximize the minimum over all these possible diversities. When we partition a community, it turns out that there is always one part of the community that will have a diversity worse than the original diversity. So this number here is always at most the diversity of the whole community. So that's our goal. We would like to maximize this minimum to attain this diversity. Notice that this is a max-min problem, and it's kind of similar flavor to what we would find in the max-min fair allocation problems. Now, to give you a little bit of intuition of how we approach this problem, we use a kind of geometric approach. So if we plot the vector B of number of types in the plane or in other higher dimensional space, any partition of the community into K parts is nothing more than a line, piecewise line joining 0 and B, where the breakpoints indicates the number of parts. So here, for example, I want 3 parts, so I only need to find 2 breakpoints. So diversity is the ratio of norms. Can be rewritten as this formula here, and this theta value is nothing more than the angle between the vector x and the vector of 1. So to maximize diversity, we would like to be close to the vector of 1, but at the same time, we would like to be adding up to the vector b. So that's basically the problem that we would like to solve.
Sebastian, in the interest of time, just a reminder that you have about 1 minute left.
Okay, I'm so sorry about that. Okay. So let me just go real quick over the first question. So when can we guarantee the maximum diversity? It turns out that the answer is very simple. You can guarantee the maximum diversity when the greatest common divisor of the B's is at most K. The main intuition here is that when the greatest common divisor is, let's say 2, then you can find points in between the line joining 0 and B. That allows you to split the vector B into parts that are exactly the same as B. But when you don't find points in the line joining 0 and B, then you have to go outside, and that basically deteriorates the diversity of one of the possible parts. In order to address this, I probably won't have time to do it now. But what I would like to say here, okay, I'll close with this, is that we have a recursive algorithm We start with this original setting. We would like to find K points here. And then we are able to reduce the instance to, let's say that we want to find 3 parts. We are able to reduce these to a smaller instance where we can map back the points that we find here appropriately to the original instance. And this can be done in an efficient time and in the input. Yeah, with that, I would like to close. I'm so sorry. Maybe I spent too much time at the beginning. Yeah, if you have any question, please go ahead.